our afternoon sessions. So we have Anupam Prakash talking talk about the quantum SDP, so the interpolynomial method.
Okay. Thank you. So I'll be speaking about a quantum interior point method for LPs and SDPs, which is joint work with Jordanis Karinidis. So let's begin by recalling an SDP. So a semi-definite program in SDP is an optimization problem. So the inputs are a vector C, which is of dimension m, and matrices A1 through AM, and B, which are n-dimensional matrices. So there are two parameters in this problem. So the first is the dimension of the matrices, which is n, and the second is the number of constraints, which is m, and we assume that these A's are linearly independent. This we can do without loss of generality, so m can be at most n squared. So the primal and dual STP are given next in the next two equations. So the primal STP is the problem of finding the optimal value of C transpose X subject to a constraint that the summation of xk ak is greater than b, whereby greater than we mean the PST ordering, so we mean that the difference of xk ak minus b is a positive semi-definite matrix. And the dual problem is to maximize the trace of by, where y is constrained to be PST, and the trace and their linear constraints trace y aj equal to cj. So for all of this talk, we'll be working in the setting where these primal and dual solutions, these primal and dual problems are strictly feasible. So there is a solution such that the inequalities are strictly satisfied. And in this case, we would have strong duality, and in particular, the optimal value of the primal will be equal to the optimal value of the dual. So linear programs are a special case of STPs where the AIs and B are diagonal matrices. So if I just plug in diagonal matrices in the previous formulation, I would get the standard formulation of an LP. So I would get summation xi ai is greater than b, where now by greater than we mean that all the coordinates are positive. So the linear program is a special case of the STP for the diagonal matrices. So whatever we say for STPs will also translate to the LPs that way. So STPs are interesting because they are one of the most general class of optimization problems for which we have provably polynomial time efficient algorithms. And further, they do capture a very large class of convex optimization problems, and they are used for approximate solutions to NP-hard problems like the max cut as we saw in the morning. So let me recall a bit about the algorithms for the STP in the classical and the quantum case. So the running time for all these algorithms will be given in terms of m, n, and epsilon. So m is the number of constraints, as we said earlier. N is the dimensionality of the system, and epsilon is the error to which we recover the solutions. And we'll be focusing here on the case where m is order n squared. So there are very large number of constraints. So there's also the case of sparse STPs, but here we'll be talking mostly about the case of dense STPs where m is order n squared. So the first polynomial time algorithms for LPs and STPs were obtained respectively using the ellipsoid method and the interior point method. So the ellipsoid was the first polynomial time algorithm for LPs. The interior point method was proposed in the 80s to improve the running time of the ellipsoid method. And later it was found that STPs also have a polynomial time algorithm via the interior point method. So the best state-of-the-art classical algorithms for LPs and STPs respectively have complexity n 2.5 log 1 over epsilon for the LPs. And for the STPs, they're a bit more complicated. It's order m cube plus mn omega. So omega is the exponent of matrix multiplication, which is less than 2.37. And so in the worst case, the STP algorithm is like order n to the 6, so which is a large polynomial. And the LP algorithm is n 2.5. So these interior point algorithms have a dependence on the error which scales as log 1 over epsilon. So apart from the interior point methods, they are the first order multiplicative weight based Arora-Cayley method for the STP solving. And its complexity can be upper bounded in the classical case by this expression. So it is n times m times s, where s is the sparsity of the number of non-zero entries in the input matrices. And then there's a width parameter RR over epsilon, which appears to a polynomial power. So this is an upper bound on the classical complexity of the Arora-Cayley method. Of course, it can do better in certain special cases. So the Arora-Cayley method is also interesting because we have had quantum STP solvers based on it. So let's summarize about the quantum STP solvers which are based on the Arora-Cayley framework. So they were first proposed by Brandau and Spohr, and then improved by Van Appeldoorn, Gribling, Gillian, and de Wolf. And we saw them in the morning. So, and recently these algorithms have been improved even further. The running time has been decoupled and improved greatly. So the best known algorithm, the quantum STP algorithm using the Arora-Cayley framework, has the following running time. So it has a square root m plus square root n times the width to the power 4, and another factor which can be at most root n. So, and also we know that for combinatorial problems like max cut and scheduling STPs, the width parameter, this RR over epsilon, is at least linear.
I'm confused. What is this less square root of n thing?
So there's the, so this is in the operator model. So there's a factor which they call as alpha, right? And this can be at most square root n.
But if you put this r and small r, you don't need that, right? So there's also runtime without this, right? So I don't think you have this square root of n, like, if you have this r over epsilon to the 4, right?
Okay.
So I don't think it's there, but yeah.
Okay, so
Right, so for constant capital R, small r, and epsilon, then you need the runtime is square root of n plus square root of n, right?
I see.
Which you wouldn't get from this, right? I think it's just not that it's fine as square root of n.
Okay, let me check that up. But
Okay, sure.
so for max cut and scheduling LPs, it's known that RR over epsilon is at least linear. So if we plug in an n, the best case running time would be order n 5.5 if Fernando is correct, and otherwise order n6. So still a fairly large polynomial in n. So here we take a different approach. We try to quantize the interior point algorithms. And this is the algorithm we obtain. So let me say its running time and all the factors which appear in it. So we have one algorithm for STPs and another for LPs. So for STPs, the running time is n 2.5 mu times k cube times log 1 of epsilon divided by psi squared. So I'll explain what all these things mean in the following. So the output of our algorithm will be a pair of matrices SY. So they'll be classical matrices S and Y, and they will be epsilon optimal. So by epsilon optimal, I mean that the duality gap would be at most epsilon. And they would be xi approximate. So by xi approximate, I mean that the STP constraints will be satisfied only to an error xi. So the output of the algorithm would be comparable to the classical STP solver. It will output a pair of matrices which are roughly optimal, epsilon optimal in sense of duality gap and xi optimal in terms of the constraints. So this factor mu comes from linear system solvers. It comes from quantum linear system solvers. So in the case of STPs, we need to solve very large linear systems which are n squared by n squared in size. And this factor mu is the square root of the dimension of the system being solved. So it is at most square root 2n for the STPs.
What is psi approximate? Have you defined it? I forgot or not yet? Psi approximate solution. What it means?
Yes, so it means that you have the STP constraints like S belongs to L minus B. So I will give you answers S belongs to L minus B prime, and B minus B prime norm would be bounded by psi. Yeah. So okay, now this parameter kappa is the condition number, but it's an upper bound on the condition number of the intermediate matrices that arise in the interior point method. So, so it's like an upper bound on all the matrices which will arise in your iteration, all the solution matrices. And so the upshot is that if the intermediate matrices are well conditioned, like if this condition number is independent of the dimension or has a very small dependence on n, then we do obtain a polynomial speedup, and the running time scales as n 3.5 for the SDPs and n squared for the LPs. So
sorry, just to clarify, for Maxwell, for example, psi, how is more you have to choose psi? You have to choose psi like 1 over n, right? Or
let's come to it later. So there are a couple of options about psi.
okay, sure.
Okay, so there's a much larger potential speedup for the SDPs because linear systems involved are much larger, and for LPs also it has been heavily optimized in the classical setting. Like the best LP algorithms are much cleverer than the best SDP algorithms. But also I would like to say, like, this is really a worst case speedup is what one would aim for. So one can hope that one could, like the result indicates that there's a potential for getting polynomial speedups for these problems. So, okay, so now let's discuss the input models in which our algorithms work, because that's very important in the quantum case. So, so the first input models for solving SDPs was the sparse oracle model. So this appeared in the first 2 papers on the subject. And here we assume access to the AIs, the input matrices. They assume to be S-sparse, and we assume that there's oracle OA, which given I, K, and L gives me the index of the Lth entry. So there's an efficient way to compute the in the matrix AI the Lth entry in row K. So that's the sparse oracle model. And then there's a quantum state model where we have access to the purifications of corresponding density matrices. Like we write AI as a sum of PST matrices, and then we assume we have access to the purifications. And the third input model is the operator model, where we assume that we have access to what's called a unitary block encoding of the AIs. So what's block encoding? So it's a unitary matrix UJ, which has a scaled version of AJ in the top left corner. And we assume that we can efficiently implement this unitary UJ, like there's a quantum circuit that implements UJ for me. So the operator model will be the most relevant for this work. So we'll be thinking mostly about the operator model. And and Gillian and Appledon also show that the other models can be viewed as a subcase of the operator model, like it's more general than others. So the next question which arises naturally is how to construct these block encodings for arbitrary matrices, and what should be the value of alpha, the normalizing factor alpha in the top left half. So one of the most general ways to construct the block encodings is to use the QRAM data structure model. So let me explain a bit about this model and how it helps us to create block encodings for arbitrary matrices with good parameters. So for the QRAM data structure model, we assume that we have access to an efficient data structure. So I'm going to define what efficient means in a bit. Storing the matrices AI, so all these in a quantum random access memory. So quantum random access memory is a device which allows the following queries in time polylog n. So if xi are stored, if there are n data points xi which are stored in the QRAM, then it allows me to make queries of the form I0 goes to Ixi in quantum superposition. So the standard oracle model also makes similar queries, but there one can implement it efficiently if there's a succinct circuit for computing the xi's from I. So the QRAM is a more general purpose device that works for arbitrary data. It has a large circuit size, but it's universal that it works for arbitrary data. So let me define what an efficient QRAM data structure would mean. So a QRAM data structure for storing a data set D of size n, I would call it efficient if it can be constructed in single pass over the entries that are being stored. Like it looks only once at the entries I, di. And And the update time for this data structure is polylog n. So each insertion or change in value or update of the data takes time polylog n. So we have solutions with time log square n for every update. So so the QRAM data structure is efficient if it doesn't incur additional overhead over sequential storage in memory. So this is a natural definition for efficiency. Like, so there is some overhead in going over the data set once, and that's all the overhead we incur in putting this into memory. So it was first proposed to address the state preparation problem in quantum machine learning. So to prepare arbitrary vector states without incurring square root n overhead as would be needed by the search lower bounds.
So just a comment about that.
Yes.
Actually, there's the QRAM model is specifically described even in Nielsen and Schwang before that.
Yes.
When they talk about implementation with the Grover oracle. So the structure was known well before QML actually.
Okay.
Totally irrelevant, but thought I should mention.
Okay, but so I would like to say in response to that that the problem becomes particularly relevant for QML because the data sets are unstructured, and there's nothing else you can do if you want to handle unstructured data sets and try to get a classical speedup. So even if it was known, it's good to rediscover it in that sense. And I don't know of any other alternate solutions which could work in this setting. Okay, so apart from vector state preparation, the nice thing about the QRAM data structure model is that it allows you to get very efficient linear system solvers using quantum walks. So let's return to the problem of block encoding and ask the question of what is the best alpha that one could hope to obtain. So the best optimal value of alpha that one could hope to obtain is 1 because the spectral norm of any minor of a unitary matrix is at most 1. But we cannot obtain such a good alpha, as we'll see. So the target would be to get alpha equal to 1. That would be the best one could hope for. But so let's also see the quantum linear system problem, which is to which is given a matrix A to and a quantum state B to produce quantum states corresponding to the matrix product AB or the matrix inverse A inverse B, the solution to the linear system. So this problem is scale invariant. So we can assume that that the spectral norm of A is indeed 1. So let's define a certain value of the mu A, like the parameter in the block encoding. So this is what we can show, that there are efficient QRAM data structures that allow a block encoding for arbitrary matrices with alpha equal to mu A. So what is mu A? It is the minimum of the Frobenius norm and this weird-looking quantity, which can be thought of as the maximum L1 norm. And so let's look over the definition of this SPA. So it's a maximum over the rows of the pth power of the LP norm. And then we have an square root of S2PA times S1 minus 2PA. So simpler way to think of it, so if we specialize to p equal to half, we get the maximum L1 norm of the rows. So all this is all under the assumption that the matrix has been scaled so that the spectral norm is 1. So in previous papers, we showed that there are efficient block encodings for A with alpha equal to mu A. And one can see that this mu A is actually sublinear and at most square root n. So this is easy to see from the Frobenius norm. So the Frobenius norm is the sum of squares of all the eigenvalues, and as the spectral norm is 1, all these are less than 1. So A Frobenius is less than square root of the rank, in particular less than square root of n. So there will be a different data structure which achieves each of these possible mu's, and they can be constructed in one pass over the input matrix. And the main result that we would like to carry on from these previous works is that given an arbitrary matrix, one can produce a block encoding with alpha equal to mu A, and that mu A is sublinear at most square root n. And okay, so here I would like to state the open problem to improve the mu A to like the best possible value of alpha one could hope for is 1, but what we know is square root n, so it would be interesting to lower this. So let me now state the results on the linear system solvers in the block encoding framework. So these are very relevant for the interior point method because the method basically solves iteratively a collection of linear systems. So these are the main technical tools that will be going into the method. So in the QRAM data structure model, there are linear system solvers. So these are the ones based on phase estimation and amplitude amplification. So they have running time mu a times kappa squared a, where kappa is condition number, and 1 over epsilon. So, and these have been very recently improved. So now the optimal linear system solver in the QRAM data structure model has running time mu a times kappa a times log 1 over epsilon. So that's the running time for one particular linear system solver. So we would also need to compose two different linear system solvers. So given block encodings for matrices M1 and M2, which are different and which have parameters mu1 and mu2, then the linear system in M, which is a product of M1 and M2, can be solved in time mu1 plus mu2. So the mu factors add, and the kappa is the kappa of the product. So it's kappa M times log 1 over epsilon. So we'll be needing this kind of composition of linear systems, and we'll be using this this much improved linear system solver, which has a log 1 over epsilon dependence on precision. And so the motivating question for these interior point methods and applications of linear system solvers is that classical linear system solvers are quite versatile. Like, they can be used to solve optimization problems using iterative methods, but iterative methods are somehow much harder in the quantum setting. So the question one would like to ask is, can quantum linear system solvers be used similarly to get speedups for a large number of optimization problems? So that's something that we have been working on. So in some previous work, we made partial progress, where we gave a gradient descent algorithm with affine update rules. And in this work, we give a second order method, the interior point method, which works for LPs and SDPs. And at a high level says that optimization is not that much harder than the quantum linear system solvers. So, okay, so now let me turn to the interior point method, and I begin with an overview of the classical interior point method. So the classical IPM starts with feasible solutions to the SDP and updates them iteratively.
Sorry, can you just remind what S and Y are?
So S and Y are the primal and dual SDP solutions.
Oh, primal and dual, okay.
So the classical IPM, it starts with some feasible solutions, SY, primal and dual for the SDP, and updates them iteratively, like S goes to S plus ds and Y goes to Y plus dy. So the updates ds and dy are obtained by solving a very large linear system, n squared by n squared linear system, which is called the Newton linear system in the literature. So the problem is that the matrix for this Newton linear system is not straightforward to write in terms of the data. Like, to write it entry by entry would require quite heavy computations, and it's also a very large matrix. So it's expensive to compute from the data. So one needs to find ways of computing it efficiently in the quantum setting. And so each iteration of the quantum of the classical interior point method solves a linear system and updates the current solution. And this continues for square root n log 1 over epsilon iterations, and then it succeeds in lowering the duality gap to epsilon. So it gets a solution with duality gap epsilon. So that's the high-level structure of the classical interior point method. So let's write it as an algorithm. So the first step is to find a feasible initial point. So this, in fact, can be done in a manner similar to the interior point method. It's well known classically. And then starting with this initial point, one writes and solves the linear system and then updates the solutions. And this goes on for square root n log 1 of epsilon steps, and the duality gap is epsilon in the end. So that's the high-level structure of the classical interior point method. So let's see what extra things come up in the quantum interior point method.
So can I have a quick question?
Yes.
So what's exactly the interior point method you're using? Because there are many, classical.
Yes, so we are using one by Nemirovsky and Benthal.
So how would I do?
So it works for the case of dense SDPs. Like it's
that would be specific interior point method for SDP.
No, it can also be applied to LPs and the SOCPs.
Okay.
So, but there are also specialized interior point methods for the sparse SDPs. By sparse, I mean the number of constraints is m equal to or the n, and many other methods. So this is one which is, so this is the one which we quantize here. So it's a particular method based on Nemirovsky and Benthal.
Actually, basically my question is that I believe there's certain interpolation method that you don't, it's more harder than just solving a linear system for each state update. So that's why I'm curious.
So writing the linear system itself is non-trivial. That's one thing.
Yeah, but I just think there are interpolation method where the update, I think goes beyond just solving linear system. It's not,
I see.
Yeah.
Okay, let's discuss this. Sounds interesting. So let's see what are the additional things that come up when we try to quantize this kind of method in the quantum setting. So first one needs to create block encodings for the Newton linear system matrix, which would allow us to solve this linear system with low cost. So this is non-trivial. One needs to construct it from the data with as less cost as possible. But the more important thing is that to construct the next linear system, we need the classical values of ds and dy. So we need to write down ds and dy as classical vectors to even write the Newton linear system for the next iteration. So we need to do tomography after each step of this interior point method. So we give a linear time tomography algorithm that's able to reconstruct a d-dimensional state with error delta in the L2 norm, with complexity d log d over delta squared. So this is not a pure state tomography algorithm, but it's specialized to vector states, and it's almost the best complexity one could hope for in the setting.
Specialized to what?
To vector states, the states with real amplitudes, and also it assumes that you have a unitary that prepares for you the state. For example, the linear system solver. Okay, so further we need to see what precision do we want to do tomography with, because there's a 1 over delta squared dependence on the precision. So it turns out that the classical analysis of the interior point method shows that if you take delta to be 1 over kappa y, where y is the current solution matrix, then your method converges at the same rate as the classical one. So this is another important part of the analysis, like the tomography precision really has to be just 1 over kappa y. And it's because of this tomography that we have this Xi approximateness in the quantum setting. Like if the linear system solver was exact, one would recover a perfectly feasible solution to the SDP. But because we have this tomography, there's an additional Xi error for these solutions. So the main technical things that we need to know to do the quantum interior point method is how to construct the Newton linear system solver, the Newton linear system matrix, how to do the tomography with nearly linear time, and the points about the analysis which tell us what the precision of the tomography should be. So let's look schematically at the quantum interior point method, just as we did with the classical. So it starts with a feasible initial point, which we stored in the QRAM, let's say. And then we repeat for t iterations. So this t is same as the classical case. It's square root n log 1 over epsilon, and output the final sy in the end. So when solves the linear system, the Newton linear system to a very high accuracy, this gives us the state ds circle dy. By circle I mean concatenation. So then we estimate the norm of ds circle dy and perform tomography and write these things classically, and we update y to y plus dy bar, s to s plus ds bar, and store in the QRAM, and then we continue. So the main tools going into it are the efficient Newton linear system solver and the tomography algorithm, and of course there's analysis which tells us what precision we should take the tomography for.
So you need the tomography to estimate the norm. That's why you
the norm estimation is a part of the linear system solver. The tomography is to get from the quantum state ds a description of the entries of ds, so that I can update s goes to s plus ds. So I update my QRAM data structure with the information I gain from the tomography.
So you really need to know all the details about the state.
Yes, so I need to have some bound on the precision, like so the tomography algorithm will give me an approximation which is delta in the L2 norm, and it will scale like 1 over delta squared. So a part of the analysis will tell me that this delta should actually be 1 over kappa y.
Sorry, I got confused the errors. So before there was epsilon, which was one kind of error, and psi was another one. Another is delta, right? Can you just remind me what all the errors are, please?
Yes, so there are 2 error parameters. So there's epsilon, which is the final duality gap.
Epsilon is like, okay.
And there's xi, which is how well the constraints will be satisfied in the end.
Okay, so they all satisfy plus psi. I just see error of psi, is that right?
Yes.
Okay, and now this delta, how it relates to this delta you have here now?
Okay, so I'm writing delta because it's coming from the. Okay, so I'm not precisely stating it here. Maybe I come to it later.
Ah, okay.
So one thing you could remind me about, so you mentioned that you avoid pure state tomography for this,
Mhm.
but wouldn't that give you exactly what you want and have very similar scaling if you use compressed sensing?
So the problem is that I need a linear time algorithm. If the reconstruction problem in the compressed sensing is solving another optimization problem, then it's too expensive for me.
Oh, so you're worried about the classical runtime swamping the quantum?
Yes, yes.
Compressed sensing is usually like solving STP, right? The classical part.
Yeah, that's fair.
Still get it.
So I really need a linear time algorithm. Like it's too expensive for me if it's even quadratic. Okay. Okay, so let's look at this runtime for the STP and decouple it into the various things that contribute to it. So as we said before, it's n2.5 mu kappa cube times whatever. So one factor is coming from the number of iterations. Like it's the same as classical, n square root n times log 1 over epsilon. So this will be multiplied to everything. So in each iteration, we are solving a Newton linear system solver, which has size n squared. So the quantum linear system solver will have complexity mu kappa log 1 over epsilon. So this mu again will be at most n because it's an n square dimensional system. So there are square root n iterations. In each iteration, we solve a linear system solver with complexity mu k log 1 over epsilon. And then we do tomography to precision 1 over kappa. So the complexity will be n squared kappa squared over xi squared.
Why n squared?
Because the state has dimension n squared.
Yeah.
And we need it to precision kappa, 1 over kappa. So that's why kappa squared. Okay, so when you multiply all these things out, then you get.
Wait. And psi appeared only in the tomography? Why did you have this 1 over psi squared in the tomography part?
So yeah, so because it's like the log 1 over epsilon is almost the same as the classical. Like that's talking about how much the duality gap gets reduced. Like all the other errors are due to the tomography part. It's something like that.
No, I know, but this psi, you introduce it only when you do this tomography, right? So this is related to some error in tomography or? Right, I see, this is the precision of the tomography, right?
This is the precision for the tomography. And then it will imply that your constraints are a bit. Okay, so for the rest of the talk, let's see how much time I have. So I'll try to sketch the technical parts of it, like and give you some intuition about it. So I'll tell you how to do tomography in linear time. Then I'll say how the classical interior point method works and how its analysis needs to be extended to get the quantum interior point method. And then finally, I will say how do we construct these Newton linear system solvers and in the quantum setting. So let's look at tomography, which is sort of independent from the rest of the discussion, but it's a nice problem. So the problem is vector state tomography. So given a vector x and rd, we can create the vector state, which encodes x in amplitude. So it is xi times I is the standard basis, and we assume that this vector state can be prepared efficiently. So we have access to a unitary U that prepares copies of the state x. And we need to learn the, so let's contrast it with the pure state tomography. So for the vector state tomography, we just need to learn the signs. Like the xi's can have plus minus 1 signs. In the pure state tomography, they can have arbitrary phases, e power minus 2 pi theta I for each I. So Sine estimation is somehow easier than doing a complete phase estimation. So here's the main theorem. Like there is an algorithm with both time and query complexity d log d over delta squared, which produces an estimate x tilde with L2 error delta, and it succeeds with probability 1 minus 1 over poly d. So it's also important that we succeed with high probability. So the algorithm is very natural. The analysis is a bit harder, but the algorithm is natural. So one takes n, which is d log d over delta squared, or 36 d log d over delta squared copies of x in the and measures them in the standard basis. So we obtain estimates pi, which is the frequency of outcome I, and we store these things. So pi is ni over n. So the problem is that these pi's are the squared amplitudes, and what we need is the square root pi. Like what we really need to estimate is square root pi, which should be xi. Like pi is xi squared. So after having estimated the standard basis outcomes for these n copies of x, we store our estimates in the same QRAM data structure so that we can prepare the state square root pi I. Okay, and now we want to do sign estimation. So we create the concatenation of the states. So we create x concatenated with the square root p state, and then apply a Hadamard. So when you apply a Hadamard, in the fourth step you can see, it adds up the amplitudes. So you get xi plus square root pi with 0i, and xi minus square root pi with 1i. So if square root pi was exactly equal to xi, you can see that one of these outcomes would be amplified and the other would be completely destroyed. So okay, so now the idea is simple. We take another n copies and measure in the standard basis and see which outcome is occurring more frequently. So if 0i is occurring more frequently, we know the sign is plus. If 1i is occurring more frequently, we know that the sign is minus. So we measure another n copies. We keep a record of whether 0i or 1i occurs more frequently and decide the sign accordingly. So there are two parts to it. One is the amplitude estimation and one is the sign estimation, and then we output the vectors.
If it's like a complex vector, then you wouldn't like do some phases, something similar, instead of just binary plus and minus?
Yes, so I think the main constraint is that one needs to have a unitary which produces x for you.
I see.
But that happens to be the case when one has a linear system solver, so it's good for this setting at least. So, like, I think it's possible to do something about the complex phases, but the real constraint is the. So let me say a bit about the analysis, how it goes. So actually, it's if one does a straightforward analysis, it's easy to get d log d over delta 4 algorithm. So let S be the set of the large coordinates. So they are all the coordinates I and d, so that xi squared is bigger than delta squared over d. So S is chosen this way so that the complement of S has very small fraction of the L2 norm. So S bar has delta squared fraction of the L2 norm. So now it's a series of three claims which follow from concentration bounds and the Chernoff bounds, but the probabilities have to be analyzed carefully. So the first claim is that the sign will be estimated correctly for all the i's in S. So there's a dichotomy. We split into S and S bar, and then we say that the estimator is good for S, and then we bound the S bar. So here are the three claims that go into the analysis. So the sign is correct for all I in S with high probability. Then for all I in S, you really have a, like square root pi estimates xi with good error. And then the third claim is that the sum of the frequencies in the complement is small, like it's at most 2 delta squared. So one can do the error analysis using these three claims. So the error is xi minus sigma I square root pi squared. So this one can split into a sum over S and sum over S bar. And from claim 2, we know that the sum over S is bounded, like it has norm at most delta squared. And when we look at the sum over S bar, we can use the MGM inequality and then get and then combine everything to get 7 delta squared for this entire error. So Okay, so that's just a high-level overview of the tomography analysis. So I'm skipping many of the details. Okay, so now let's turn to the classical interior point method and see how it works. So let's begin by recalling the primal and dual STPs. So it's the same as before. So let's introduce some notation. So let L be the span of all the AIs. So it's the span of all the input matrices, and let L perp be the orthogonal complement. So this L is a matrix space, like it's a space of n by n matrices. And let C be an arbitrary dual solution, and let S be what's called the slack matrix. So it is xk, ak minus b, which is supposed to be PST. So the first step to get the classical interior point method is to reformulate the STP into a more symmetric geometric form. So we write it as trace, as minimizing trace CS plus where S belongs to L minus B. So it takes a bit of work to see that it's actually equivalent, but it's a good exercise. So with the new formulation, we have symmetric constraints for both the primal and the dual. So we have S belongs to L minus B, and Y belongs to L perp plus C, and they look exactly similar. So another advantage of the new formulation is that we have a very simple expression for the duality gap, which is the difference between the dual solution and the primal solution. So as S plus B belongs to L and Y minus C belongs to L perp, we have that the trace of these two is 0. And when we expand this out, we get that trace Sy is exactly the duality gap. So there's a very simple expression for the duality gap. So now we need to define what's called the central path. So for this purpose, we introduce the logarithmic barrier, which is kx is minus log det x. And the central path is parameterized by a single real number nu, a positive real number nu, and it's given by solutions to the following convex programs. So it's the same as the STP, apart from the fact that we have added nu times the log barrier to the objective function. So one can see that as nu tends to 0, we tend to the STP. Like if nu is equal to 0, we have exactly the original STP. And if nu is infinite, then the original objective function is ignored completely, and we are just trying to optimize log barrier over this constraint set. So the idea for the interior point method is to start with a high value of nu and to reduce it iteratively. So in each step, you get a solution with a smaller value of nu, and when one obtains solutions for nu tending to 0, we recover solutions that are close to that of the original STP. So the central path is well defined and unique, and it also has a very nice characterization of the solutions on it. So a pair of feasible solutions, S nu and Y nu are feasible, are on the central path if they are feasible and this identity holds. So S nu times Y nu should be equal to nu times identity, and vice versa. So of course, the ideal interior point method would just follow the central path in the direction going to 0, but the actual method tries just to stay close to the path. So we need a measure of the distance from the path. So here, the following distance measure is used in the analysis. So it's I minus nu inverse S half Y S half Frobenius squared. So from the previous characterization of points on the central path, it's easy to see that this distance is 0 if S and Y lie on the central path. And further, there's a nice characterization which relates the duality gap and the distance. So it says that the trace Sy, which is the duality gap, is bounded both ways by this distance. So it's nu times n plus square root n times the distance, plus minus. So this inequality tells us that it's enough to stay close to the central path. So if I have a pair of solutions Sy with the distance at most eta, where eta is a constant, then this trace Sy is going to be less than 2 nu eta. So if the d is a constant, then it's the trace Sy is really close to nu eta. So let's see the main step in the analysis of the classical interior point method now. So with all this background, we can formulate and see the main step. So so it starts with a pair of feasible solutions, like this is an invariant. So it starts with a pair of feasible solutions with a certain duality gap. So trace Sy is nu n, and the distance is less than eta for some constant eta. And the goal is, in a single step, to decrease the duality gap, to find a pair of solutions S prime, Y prime, with a smaller duality gap, with nu prime, which is 1 minus a constant times square root n times nu. And to maintain the distance as before, like d Sy nu should remain constant and the duality gap should decrease. So we need to find updates which does this, and the way to find these updates is to add a nonlinear constraint and to write the linear system which corresponds to the first order Taylor expansion of this nonlinear constraint. And that's how the Newton linear system comes up. So the Newton linear system actually has a simple form. So it says that ds should belong in L. So L, remember, is the span of all the input matrices. dy should be in L perp. And dsy plus s dy should be nu prime I minus sy. So again, this Newton linear system is quite natural. It comes up from adding a nonlinear constraint and then taking the first order Taylor approximation. And the main statement in the classical analysis is the following, that the Newton linear system has exactly one unique solution, ds and dy. The updated solutions, s prime and y prime, remain positive definite. And the distance remains the same. Like if we start with the pair of solutions which are at distance eta from the central path, the same remains true of the updated solutions. So that's the classical interior point method. So one sees that the same invariant is maintained, and in each iteration the duality gap is going down. So in square root n iterations, one converges to a duality gap of epsilon. So in the quantum method, one needs to analyze this classical method in an approximate setting. So we don't have the solutions dy and ds to the Newton linear system, but we have reconstructions of them from the tomography algorithm. So we have dy bar, where dy minus dy bar Frobenius is bounded by something. And then we are writing the same Newton linear system and using these ds bars and dy bars as the updates. So we prove the following, that the updated solution, even for this approximate setting, is positive definite. Like s bar is bigger than 0 and y bar is bigger than 0. And it continues to satisfy that the distance of the updated solution is less than eta from the central path. And the duality gap goes down by a constant. So the difference is that the constant is much smaller in this approximate setting than the classical one. So for the classical method, you would have chi. Here you have something smaller than chi, which is between 0 and chi. So it's like the rate of decrease of duality gap goes down, but all the other good things continue to hold. And so the same analysis works. So the analysis also gives you the precision you need for the tomography algorithm, the proof details that come up in the analysis. So lastly, I'll try to show you, give you an idea of how to solve the Newton linear system in the quantum setting. So if we write the Newton linear system as given, like as ds and dy, then we have a certain constraint. ds belongs to L, which is hard to express as a linear constraint. So this is because we have a basis for L, but we don't have a basis for L perp. And to compute a basis for L perp would be very expensive computationally. So we switch to the variables, like we change variables to dx and dy, where dx and ds are related as before. And then we try to compute what exactly this Newton linear system matrix looks like. So it has a block diagonal structure, like I've written it down here. So one can see that it has roughly 4 blocks. And each of these blocks, we will see that we can have efficient block encoding for it. So now let me say how we try to get the block encoding for the Newton linear system matrix. So the main idea is to factorize it as a product of 2 matrices for which we can get a good block encoding. So the factorization is given here. So it is, so I'll explain what this notation means in a moment. So I'm using these matrices y tilde and s hat. So these are okay. So for any given matrix Z, one can define Z tilde to be an n squared by n squared matrix. So the original matrix is n by n. This Z tilde is n squared by n squared, and it has the rows given by I tensored Zj, and Z hat similarly has rows given by J tensored Zi. So the point about them is that Z tilde is a block diagonal matrix with n copies of Z on the diagonal, and Z hat is a permutation of Z tilde. So the first, so to solve the linear system, the first step is to note that this factorization actually holds. And given this factorization, now the problem reduces to constructing block encodings for M1 and M2. So now if you look at M1, it is y tilde, which is a block diagonal matrix with y on the blocks, and Im, which is the identity matrix. So we already have y in the QRAM data structure, so we know how to construct block encodings for M1. This is easy. So the main challenge is to construct the block encoding for M2. And for this, we have to see the structure of M2, like what exactly are its entries, how can we hope to construct them. So M2 has this block structure. So the A's are already available to us. The A's are the input matrices. They are stored in efficient ways in the QRAM. So the main part that we need to address is this y inverse S hat. And fortunately, it turns out that this matrix has rows and columns, which are exactly the tensor products of S and y inverse. So you take the rows of yj of y inverse and S and take the tensor products, and you get the rows of this matrix y inverse S hat. So to create a block encoding for M2, one needs to compute its rows and columns efficiently. And this we can do if we have S and Y inverse in the memory. And so I showed you how to construct the block encodings for each of the blocks. So we also need to compose them. So we need an additional lemma which says that if I can prepare the vector A and the vector B, I can also produce the concatenation in time, which is like Tu plus Tb. So, okay, so there are a large number of details that I don't have time to go into, which is, so I particularly skipped how to get the precision for the tomography, how to deal with linear programs, and like we switched variables to dx and ds. So how do we recover ds given the dx? So combining it with the analysis of the approximate interior point method, one gets the guarantee that trace sy is at most epsilon, like the duality gap is bounded. And the solutions are approximate in the following sense, like the final solutions you get, sy belong to L minus B prime and L perp plus C prime. And there's a relative error approximation for these. Like B plus C minus B prime plus C prime in the Frobenius norm is zeta times B plus C Frobenius. So one can also get an absolute error zeta at the cost of blowing up the running time by square root n. So yeah, sorry, I might have gone too fast, but I had to keep in touch with the time. So let's conclude with some open questions. So for what optimization problems could one hope to get a polynomial quantum speedup? So that seems to be a very interesting question. So for this one, would like to see what the condition number dependence is for practical cases of the interior point method, because we have a large kappa cube in the running time. So another question is to find quantizations of other optimization algorithms, for example, the interior point methods for the case of sparse SDPs. So a third problem is to find better quantum algorithms for LPs. Like classically, one gets better algorithms for LPs by doing efficient maintenance of inverses. So maybe something similar can be done in the quantum setting. And there's also a classical step in the interior point method we have. Like so we are computing Y inverse classically because we needed to construct the block encoding for M2. So it would be good if this could also be done quantumly. And of course, there's a question of finding quantum algorithms for convex optimization with provable speedups, maybe for problems more general than the SDPs. Okay, so I would like to conclude with that. Thank you.
Questions?
What do you mean that in the case of sparse STPs to find the 0-point method?
So by sparse STPs, I mean the number of constraints is much smaller than n squared, say just n.
I see. Can you go back to the runtime, the final runtime, like which was in the beginning? Like, just to compare, like.
Yes.
Yeah. Okay. So, is it right the one way to think that before we had this dependency in epsilon, right? The previous methods, it was like epsilon to the 4, epsilon to the 5, right?
Yes.
But it was really bunching two different errors before, right? The duality gap with how well you approximate the constraints, now, right? And now you separate the two, and now you see this bottleneck that you have to estimate the constraint by measuring, which gives this 1/xi square. This is you have, right? But you improve on the other one, right? So kind of you, right? So this is so like different from classical, because classical solvers, you don't need this 1/xi square. Right?
Yes, so in the classical solvers, it's just one parameter, right? So
Right.
this 1/xi square is because you're using tomography and your solutions
So
are not.
this you cannot avoid, but what is nice is that you kind of separate this contribution from tomography from some other contributions of the error, and now you only have 1/xi square, right? So you improve like from 1 to the 4, right, to the 4th power to the square, right?
Yes, so the initial tomography was like power 4 and now it's squared.
Right. But then you have this n to the 2.5.
So this n 2.5 is because, okay, so square root n is because of the number of iterations, which actually could be much smaller in
Yes,
practice.
that's right.
And there's n square because of the tomography, like the state,
Square is tomography, okay.
because you are learning a large dimension state. That
And
seems
it's n square
unavoidable.
because you are actually running some kind of matrix, right? Or
So the problem is that the linear system you need to solve is
I,
has dimension n squared.
and you have some feeling for kappa, like
For
or
kappa,
or what?
so I think it should be tested out in practice. Like, how does it really scale for problems of interest?
Did you try, or do you have an idea?
So I've heard conflicting views on it. Some people say it's important and like it really matters to reduce it. Others say it works fine in practice, but I have to do it myself. Yeah.
So can you remind me, when you're running the tomography, do you use amplitude estimation in order to get a quadratic advantage, or are you just sampling?
We're just sampling for now.
So then it's conceivable you could reduce that from 1/zeta squared to 1/zeta scaling.
So maybe, and that would be interesting, and it would be quite relevant too, because it would get one of the kappas off. Like it,
Yeah,
it would
exactly.
contribute to the.
Do we have more questions? Okay, let's thank the speaker again. So we're gonna have the open question session. Actually, I'm not sure exactly what I'm gonna do. So let's see for that. But let's assume in 20 minutes. So that's yeah. So like 2:55. So we can.